Good morning, friends. Myself, Dr. Kushal Bhattacharya. Today, I should be going to discuss on rolling contact bearing. Now, it is a very important topic as far as automobile and mechanical engineering is concerned. And for the free movement of a shaft, suppose if you take an example of a shaft, if a shaft is to rotate like this, to freely at the end where it houses, there have to be some bearings so that it could move freely. So this for the free movement of a shaft, for the free movement of any rotating shaft, bearings are very much important part. So for this check we should be discussing today the first part, that is the rolling contact bearing. Now the rolling contact bearing, if you see the description of a rolling contact bearing, it consists of a inner and outer race, a rolling element, the object which is rolling inside, that can be a ball, that can be a roller, that can be a needle, and a cage which holds the rolling element, together and space them evenly, so that one rolling element does not come in contact with another, evenly around the periphery. So these are the components of a rolling contact bearing. The first one is, as discussed, the inner and the outer race. A rolling element, it could be a ball, it could be a roller, it could be a needle. And the third one is the cage, which holds the rolling elements together and space them evenly around the periphery. The figure shows of a rolling contact bearing. The outer one is the outer race, the inner one is the inner race, and within there lies the ball, and both the whole element has been enclosed in a cage which holds it together evenly, as I discussed before. Now I am coming on the types of bearing. Now depending on the rolling element, what is the rolling element? I have the second component I have told is the rolling element. So depending upon the rolling element, it could be a ball bearing, it could be a cylinder roller bearing, it could be a taper roller bearing, and it could be a needle bearing. So depending on the rolling element, it is segregated into four types, or differentiated into four types. Number one is the ball bearing, number two is the cylindrical roller bearing, number three is the taper roller bearing, and the number four is the needle bearing. Now, this is an example of a cylindrical roller bearing. You could find the cylindrical rollers are all lying all over the periphery. This is an example of a taper roller bearing. You could see the taper rollers lying all throughout the periphery of the bearing. This is an example of a needle bearing, and the needles are also lying all throughout the periphery of the bearing. Direction of the load, it is considered into two parts. One is the radial bearing and another one is the thrust bearing. This picture shows the example of a radial roller bearing. This picture shows the example of a thrust bearing. Now we come to Hodgins equation, which is an important criteria for determining the load capacity of a bearing. So this Hodgins equation is an important criteria of determining the static load capacity of a bearing. It is based on the following assumptions. So now Hodgins equation is based on the following assumptions. Assumption number one: the races are rigid, as I've defined in the following picture. What is called a race? So the outer members are called the races. The races are rigid. And retain their circular shape. So that is, as the races are rigid, so these are the races. So this one is the races. So as the races are rigid, so what happened? No deformation will take place on the races. So, and as no deformation takes place on the races, so they will retain their circular shape. So they will retain their circular shape as no deformation takes place. The balls are equally spaced. All the balls are that is the ball bearings. The balls of the ball bearings are equally spaced. So they are spaced at equal difference. the balls in the upper half do not support any load. The upper half of the ball do not support any load, do not carry any load. Now the forces acting on the inner race. Now the forces acting on the inner rolling element, which supports a static load C0. So this is the static load. This is the static load C0 is given. This is the static load C0 is given. It is assumed that there is a single row of balls. So we assume that there is no row perpendicular to the board or along this axis. That is, if it is considered as X, Y and Z. So along this axis, that is a perpendicular to the board, this axis, there is a single row of balls. There is only one row of balls. Now in this condition, it is assumed that when the load Cu is the upper, if you analyze the equilibrium condition, if you analyze the equilibrium condition, what are the forces acting over here of the race? You could see that C0 is the load acting, and another, what are the load balancing loads? Now P1 C0 is acting in the downward direction, and P1 is acting in the upward direction, and that is a reaction force. Now you see that all the reactions are given from the inner race, that is the load from the outer race coming to the inner race, and the outer race. So as we have discussed in our actual assumptions, that no load in the upper half of the ball, so only the reaction load coming from the outer race on the balls, which is acting on the inner race. Now the load C0 is balanced by P1. Now P2, now this component, cos component of P2 will act in the direction of C0. Now if you want to draw the cos component of P2, what will the P2 should be like this. Now if we draw the cos component of P2, it should be like this. If this is beta, this should be if this is beta, this should be beta. So this should be equals to P2 cos beta. Now P2 cos beta from here, this is P2 cos beta. If you draw this like this, then another load should be over here also. So here also it will act another load. So that will take P2 cos beta plus P2 cos beta, that is twice P2 cos beta. Same will happen for P3. So there will be a load acting on this direction. You can take this load acting on this direction. You can load act on this direction, but here the angle should be twice beta. So it should be twice P3 cos beta 3. Twice P3 instead of this beta. Now this angle will be twice beta. This angle will be twice beta. So what happens? The load over here should be P3 cos 2 beta. So P3 cos 2 beta from here, and P3 cos beta from here, it will take 2 P3 cos 2 beta. Similarly, if there are number of loads, it will be acted up. So it will remain like this. So it will balance the applied axial load. Now the thing is that as the races are rigid, now you have seen in our first assumption that the races are considered rigid. So as the races are rigid, deflection, as the races are rigid, so what will happen? As the races are rigid, so what will happen? Deflection of the inner race with respect to outer. Deflection of the inner race. This is the deflection of the inner race with respect to outer will be due to the deformation of the balls. So that means basically what happens? The inner race, this center, the center of this one, the center of this from this ball will come over here. Why it will come over here? The rest will be held rigid. So now how does this deflection takes place? This deflection takes place due to the deflection of the balls, because we hold that the races are considered as a rigid. As the races are considered as a rigid, the inner race and the outer race, so but still deflection is taking place. So that squeezing action is taking place due to the deformation of the balls. Now if we consider the deformation of the first ball del 1, now the displacement of now if you consider the deformation of the first ball as del 1 and consider the deformation of another ball as del 2, so from this angle beta we can easily write that del 2, this deformation is equals to del 1 cos beta. So easily, because this is from hypotenuse, we could easily say that del 2 is equals to del 1 cos beta. So in fact we are transforming this deformation del 2 in terms of deformation of the first ball. So we can write that ultimately del 2 by del 1 is equals to cos beta. Now according to Hodgins equation, what is actually Hodgins equation, I should discuss in my next topics. What is Hodgins equation? It is basically a part of contact mechanics. I should be discussing in one of my lectures. I'm not going very deep into this. I'm taking only the results of the Hodgins equation and explaining it. It's a part of contact mechanics. I should be explaining it now in the upcoming lectures. Now from the results of Hodgins equation, it is seen that the deformation is proportional to the load to the power 2 by 3. So from that we could say that del 1 is equals to C1 to the power P1 2 by 3, and del 2 is equals to C1 into P to the power 2 by 3. Now now we know that now if we put this del 2 by del 1, so C1, the constant portions cancels out and it comes P2 by P1 to the power 2 by 3. Now previously we have shown that cos beta is equals to del 2 by del 1. Similarly, cos 2 beta should be equals to del 3 by del 2. So in place of del 2 by del 1, we put the value of cos beta. So it becomes this in place of del 2 by del 1, because we know this from our previous explanation, we just put this value of del 2 by in place of del 2 by del 1, we put the value of cos beta. So it becomes cos beta. So the equation becomes cos beta is equals to P2 by P1 to the power 2 by 3. Now what happens when it becomes 2 by 3? This equation becomes 2 by 3. So basically what happens, P2 becomes P2 becomes is equals to P1 into cos beta 3 by 2. It just opposites, it just this inverse. Similarly, P3 becomes P1 into cos 2 beta 3 by 2. Now this becomes 2 beta. As you know, how why 2 beta? Because this angle is beta plus beta, twice beta. Now P3 becomes P1 into cos twice beta into 3 by 2. Now an important observation is that all the loads, that is P1, P2, has been converted in the form of P1. It has been converted in the form of P1. That is, this value has been converted in this value. Now we write that we know that our equation is equals to C0 is equals to this load C0. This load C0 is equals to this load given C0 is equals to P1 plus twice P2 cos beta plus twice P3 cos 2 beta plus dot the more number of balls are there. Now if we put the value of C0 and we transfer the values from here, in place of we actually put all the values of converted into P1. So we take a common of P1 and get the value P1 plus 1 plus twice cos beta 3 by 2 into cos beta plus twice P3 cos 2 beta 3 by 2 into cos 2 beta plus dot. So ultimately it will become equals to, if you take this a constant part m, if we take a constant m, you take this value as a constant m, so it becomes C0 is equals to P1 into m, where m is equals to 1 plus twice cos 5 by 2, because 3 by 2 plus 1 5 by 2 twice cos 2 beta 5 by 2 plus onwards. And now about the z, and now for finding out the number of z. Now z, if z is the number of balls, if z is the number of balls present in a bearing, so beta should be, the angle beta should be equals to 360 degree by z. The angle beta should be equals to 360 degree by z. Now from this equation that we have derived previously, that C0 is equals to P1 into m, that is that we derived. Now we plot a table for taking different value of z and different value of m. Now we know that beta is equals to 360 degree by z, where z is the number of balls we have discussed previously. Now we take we take various values in this column. We take the values of z, and along this row we take various values of z, number of balls for 8, 10, 12 and 15. We take number of balls, we take various number of balls. This is number of balls, this number of balls we have taken. And for m for m as the value of m depends on the beta, and as beta depends on as because if we know that m is a function, if you see m is a function of beta. Now and again beta is a function of z. So when we change the value of z, ultimately this m is affected, so for different values of z, we calculate different values of m, and we made a ratio between z and m and found that this ratio z by m is almost constant, and it is taken as 5 by Strebeck. Strebeck suggested that the value of z by m is taken as 5. So from this we put the value of the m. Instead we replaced m and we put the m if z by m is taken as 5, so normally m is taken as z by 5. So we put this value over here in place of m. We put this value and we get that c0 is equals to 1/5 z into p1. See, we get c0 is equals to 1/5 z into p1. Now from experiment we find that to produce a permanent deformation in a ball, the maximum load P1, this is from experiment, this calculate to produce the permanent deformation. The maximum load P1 is given as P1 is equals to K into D square. P1 is given as P1 into K into D square, where K depends upon the radius of curvature at the point of contact, because at the point of contact, if you see the point of contact, when we should be experimenting the Hodgins contact, we see these are the two. When the point of contact, it depends on the radius, it depends upon the radius of curvature, the point of contact, and the Young's modulus of the both materials, so from this we get that P1 is equal to K into D square. So ultimately we put the value of P, in place of P we put the value as K into D square into Z into 5. So we get that C is equal to K D square Z into 5. So this is we get the value of, this is the desired Strebeck's equation. And this is up to this part we should be discussing for the part 1 lecture of the rolling contact bearing, and the part 2 lecture it should follow the other parts, the remaining part. And so if you like my way of delivering the lecture, so please put a thumb up to it, and if you subscribe to my channel, so you can get more, and you get updated of more and more videos related to mechanical engineering and automobile engineering. Thank you. This is from Dr. Kushal Bhattacharya. Have a good day.